Assalamualaikum. I'm Muhammad Anas here. The date is 10th of December. The day is Thursday. Now, this lecture is for matter class. The subject is physics. Today's topic is properties of matter. It's chapter number 10 and it's lecture number 2 final term. Okay, let's start with the chapter's name. So, here chapter it starts with the word properties. Okay, so first I will explain you what are the properties. Properties simply means some unique features. Okay, some unique features of a body. For example, if we talk about this whiteboard here, what are its unique features? That it's smooth and plain, it's clean, it has large area. So these are the properties of this whiteboard. Okay, this is property. For this property, it simply means some unique features associated with a body. Now, if we talk about matter, what actually is matter? It simply means when something has a certain weight and occupy space. Okay, it simply means if a body have a certain weight or it has a defined space. For example, this board marker here, okay, it has certain weight and when it is placed at any surface, it's gathering a certain space here. Okay, so this is a matter. And what is not a matter? Energy, flame, electricity, these things are not matter. Why? Because they do not have any weight, they neither occupy any space. Alright, so everything here, almost everything here is matter. This whiteboard here, these walls here, the light, my wristwatch, my hand, this everything here is matter. Okay, and what actually is not matter? The energy, every sort of energy is not considered as a matter. Okay, so let's recall it again. Water properties, unique features associated to a body. Unique feature means the surface area of this whiteboard, it's clean and smooth. These are its properties. Okay, and what is matter? Anything that has certain weight and occupied space, that is matter. Okay, now in this chapter, the very first property of matter discussed here in your book is elasticity. So now I am proceeding to the next lecture, to the next topic. Okay, so the very first property here mentioned in your book is elasticity. Okay, that is the property of a matter. Okay, I have mentioned you earlier that what actually is property. It simply means some unique features associated to a body. So elasticity is the property of a matter. What actually is elasticity? So I'm writing it here. What is elasticity? The property. It's property of matter. Okay, the property of a body to regain its original shape after it is disturbed or perturbed. Perturbed is better word here. Alright, so what is elasticity? The property of a body to regain its original shape after it is slightly perturbed. What actually it means? What do you mean by perturbation or perturb? It simply means some disturbance, some sort of disturbance. Okay, for example, here this is the matter, this is the body. Okay, now when I squeeze it, I'm perturbing it, I'm disturbing it. Okay, I'm squeezing it. Okay, it has a property to regain its shape. Okay, when I release it, it will regain its shape. Okay, so that is the property of that disturb. So the property of a body to regain its original shape after it is perturbed is called elasticity. Okay, so that simply is elasticity for you. Now, okay, so the next topic after elasticity is stress and strain. Okay, so I'm going to explain you about stress and strain individually. So let's move to stress first. What actually is a stress? That simply means a certain force per unit area. Alright, what do you mean by that? It simply means that you are applying a certain force here on a specific surface. Okay, for example, if I'm squeezing it, this board marker here, so I'm applying a certain stress here. Okay, so that is stress. It simply is force per unit area. And then strain is simply deformation. What do you mean by deformation? Okay, let's consider this duster again. I'm applying here a certain stress and it is deforming. It's changing its shape. Okay, so that is deformation. After application of certain stress, it is deformed. Okay, here that is deformation is a strain. Okay, the more we apply stress, the more it is deformed. The more will be the strain. Okay, so there is a link in between then stress and strain, and that link can be written as stress is directly proportional to strain. That simply means when there is a greater stress, we have a greater strain. Okay, so now the formula for stress here is stress is equal to force per unit area. As I have mentioned earlier, that stress is nothing but force per unit specific area. So here we will write it in mathematical form as stress equals F upon A. F means force and A means certain area. Okay, now I'm moving to strain. Okay, there are three types of strain, of which just two are mentioned in your book. Okay, but I'm mentioning here all three. Number one is longitudinal strain. Number two, aerial strain. Number three is volumetric strain. Okay, so let's move to longitudinal strain first. Longitudinal strain simply means change in length per unit original length. Aerial means change in area per unit original area. Volumetric strain means change in volume per unit original volume. Okay, so that is indicating longitudinal strain. That is indicating aerial strain. It means change in deformation in area. That is, here is deformation in the length. Here in the second type there is deformation in area, and in the third type there is deformation in volume. Okay, so these are the three types of strain, and they all three have different formula here. Okay, to the next topic. Okay, so let's continue from the relation between stress and strain. As I have mentioned earlier, that stress is directly proportional to strain. Okay, that simply means that the greater the stress, greater the force. The greater the force, the greater will be deformation. Okay, the greater the force, greater will be deformation. So, if we remove this proportionality sign, we may have stress equals, and a constant will come here, and then strain as it is. Okay. Okay. If we remove proportionality sign, we always have equal to sign with a constant term. Here in this relation, constant is called Young's modulus. Okay, and it is symbolized as capital Y. So if we put y in place of constant here, this equation now can be written as stress is equals to y times strain. Okay, and if you are interested in finding the expression for y, so y will simply be equal to, I'm moving this strain, here it's multiplying, when it will move to the left side, it will divide with the stress. So the expression, final expression for y will be stress over strain. Okay, so that is Young's modulus. If someone asks you about what's Young's modulus, you will simply tell them it's simply the ratio between stress and strain. What is Young's modulus? It is the ratio between stress and strain. Okay. Okay, so I'm continuing here from this expression that y Young's modulus is equal to stress upon strain. It is the ratio between stress and strain. Okay. Now what if we put their respective values? value for stress and the value for strain, as we have discussed earlier. What was the stress? I'm writing it here. What was stress? Force per unit area. Okay, so here I have put the value for a stress, that is F over A, force per unit area. And what is strain? Strain, if we talk about longitudinal strain, okay, so that will be del L over L. As I have mentioned earlier, that longitudinal strain is the change in length per unit original length, and what was the stress? It is force per unit area. Okay, so I simply have put their respective values here in this formula. Value for a stress is F over A. Expression for a longitudinal strain is del L over L. Now let's simplify this statement. Okay, Y equals F over A. This whole thing is dividing with this whole thing, so I'm writing here this sample of division. Now let's move to this part of the board. What if we write sign of multiplication in place of sign of division? Here del and L will shuffle their position. Now F is multiplying with L, that will be FL, and that will be A del L. Okay, so that is the final expression for Young's modulus. Why? Okay, so the next topic is elastic limit. What is elastic limit? It simply is the maximum stress after which body loses its property of elasticity. What do you mean by that? I'm explaining you. Okay, the maximum stress after which body loses its property of elasticity. For example, here this is a material, this is a body. Now if I apply certain stress here, it will stretch, okay, but it has a certain limit after which it will not regain its shape. Okay, if I apply a stress beyond its limit, it will break apart and it will not obey the property of elasticity. Okay, so what is elastic limit? That is the maximum stress after which body loses its property of elasticity. Okay, and literally after applying the maximum stress, the body will break apart into two or furthermore pieces, so it will not obey the property of elasticity. Well, so our next topic is Hooke's law applied to a helical spring. Okay, so that word helical may sound new for you. That is nothing but the name of a shape. It means a helix. A helix is a shape of spiral symmetry, something like this. Okay, if something is like this in a spiral shape, that is a helix. Okay, for example, a DNA is of helix shape. Okay, so anything that is of a spring shape, so that is a helix. This is the shape for helix. So here we are discussing about a helical spring. I'm mentioning it here. There is a spring, and there I have attached a block of mass m here. Now what? Okay, this surface is rigid. It means it's fixed here. Now what if I apply certain stress here? Okay, what if I bend it? This spring. What will happen? It will eventually squeeze. Okay, after squeezing it, after I apply a certain force, a certain stress, it is deformed. Okay, now I have here applied certain stress. Now there is a longitudinal strain, there is deformation in shape. Now, okay, so if you apply certain stress here, it is deformed. Okay, after applying stress here, there is a certain strain, longitudinal strain. Now I'm writing here an expression that greater the force, the greater will be displacement from the mean position. It simply means the more I exert force here, the more I exert stress here, the more it is displaced from its mean position. Okay, this is its mean position. The more I apply stress here, the more it is displaced away from its mean position. Okay, either on the left side or either it is stretched to the right side. Okay, so here this relation shows us that the greater there is the force of a stress, the greater will be the displacement away from mean position. That minus sign indicates that the motion is away from mean position. Okay, it doesn't matter in what direction we apply force here. If I stretch it, it will move away from its mean position to the right side. If I squeeze it, it will move away from its mean position to the left side. Okay, it doesn't matter. It will always move. It will always move opposite to its mean position, away from its mean position. So this minus sign indicates that this body is moving away from its original mean position. Okay. Now let's proceed this Hooke's law. We already know that if we eliminate this sign of proportionality here, we will get equal to sign and a constant here. Okay. Now here in this case, what is a constant? Here, constant term is k. We write k here as a constant. So after putting k in place of constant, we will get F equals minus kx. Okay. So that is the final expression for force that is exerted on this block of mass m. So when force is exerted, it is displaced x times. Okay, so x that x represents how much it is displaced away from its mean position. So that is the final expression for force, and that law, that link, that relation indicates Hooke's law applied to a helical spring. So that is its expression, and that is the mathematical form of that final force. So here the statement for this law should be, so the statement for that Hooke's law applied to a helical spring is tension is directly proportional to extension. Okay, so
ये नहीं बनी शायद वीडियो बंद था
okay, so the statement for this Hooke's law applied to a helical spring is tension is directly proportional to extension. Okay, here extension is x, so it is displacement. It simply means that how much away the body of mass m moved away from its mean position. Okay, so that is extension, that is x, displacement. Here tension is stress, the force which apply to a body, the force which is exerted to a body to stretch it, to move it x times away from its mean position. Okay, so here extension is displacement away from its mean position, and tension is the stress applied force that exerted on the body of mass m. Okay, so that is Hooke's law.